Made a previous video about electromagnetic waves and how electromagnetic waves can go through reflection or refraction. Reflection meaning that electromagnetic waves are incident on a surface and then reflect back off of that surface. And so when that happens, if you were to take the surface and draw a perpendicular line to it, then the angle of incidence, which would be the angle between the perpendicular line and the line of the electromagnetic wave coming in, the reflection angle is going to be exactly the same as the angle of incidence. So in other words, like if you were to imagine this wave coming in and then bouncing back off, the total width of that would just be twice what the angle of incidence is, because the angle of reflection is the same as the angle of incidence. So that's reflection, but then you have cases where the electromagnetic wave hits a surface and then continues to propagate through that surface. And so this is where I talked about the importance of the particular substance and the rate at which the electromagnetic wave propagates through the substance. It turns out that for different materials, electromagnetic waves are going to propagate through that material at different speeds. And so this is where the whole index of refraction idea came up. And the index of refraction is defined as the speed of light in a vacuum, which is 3.0 times 10 to the 8 meters per second, divided by whatever the speed of the electromagnetic wave is in a particular medium. Now, since we have electromagnetic waves not being able to go faster than the speed of light in a vacuum, it would take an infinite energy for an electromagnetic wave that's going less than the speed of light to be able to catch up to the speed of light. So we know the electromagnetic waves, if they are born into existence at less than the speed of light, then the cosmic speed limit for them would be the speed of light in a vacuum. And so that means they're going to be, in other materials, something less than the speed of light in a vacuum. And so if the index of refraction is c divided by whatever the velocity of electromagnetic wave in a vacuum or in a material other than a vacuum is, it's going to be c divided by some number that is less than c, and that means it's going to be 1 at minimum or greater than 1. Okay, so here's the thing. It turns out that when it comes to the rate at which an electromagnetic wave propagates through a medium, it also depends on the particular frequency of the electromagnetic wave. So for example, when we think of white light is composed of different colored lights that can be singled out by the human eye. This is the whole red, orange, yellow, green, blue, indigo, violet. These are the different colors of the rainbow. And together they form white light. We perceive it as white when you see this mishmash of red, orange, yellow, green, blue, indigo, and violet. But red, orange, yellow, green, blue, indigo, and violet each have slightly different wavelengths. And if they have slightly different wavelengths, that means they have slightly different frequencies. Frequency is inversely proportional to wavelength. So the shorter the wavelength you have, the higher frequency you have, and the longer wavelength you have, the lower frequency you have. So it turns out that for electromagnetic waves that have shorter wavelengths, which is to say they have higher frequencies, they tend to move more slowly through materials than electromagnetic waves that have longer wavelengths and therefore lower frequencies. So if you can imagine, if you were to take white light and shine it on, say, glass, some of you might have seen like a prism, like a triangular glass object where you shine light in on one side and you actually see the colors of the rainbow come out on the other side. And this is a phenomenon that's known as dispersion, because what happens is that because for different frequencies of the light that makes up white, the red, orange, yellow, green, blue, indigo, and violet, it turns out that when it goes through refraction between the surface of the air and the glass, there's going to be slightly different angles at which the different colors are refracted. Because remember, when you have an interface between two surfaces, the electromagnetic wave propagating through the surface bends, and it bends in proportion to the rate at which it either speeds up or slows down when it's going from one medium to the next. In the previous video I talked about how if you're going from a faster medium to a slower medium, then the light bends more towards the perpendicular to the surface. And if you're going from a slower medium to a faster medium, again, this is how fast electromagnetic waves are propagating. If you're going from slower to faster, it's almost like it bends away, it gets away from the perpendicular. So the rate at which these electromagnetic waves are propagating the medium is going to determine the refraction angles. And so if the rate at which they are moving also depends on their frequency, then you're going to have a slightly different refraction angle for red than you say are for blue. And this is the whole phenomena of dispersion. And so again, when you have shorter wavelengths and therefore higher frequencies, then you're going to tend to travel more slowly through a medium. Okay? And so then when you think of white light, the shorter wavelengths that make up white light are the bluer wavelengths. And so the bluer wavelengths are going to travel more slowly through, say, glass than the redder wavelengths. And so what that means is that if you were to shine white light into, say, a glass prism, you're going to have the blue light not bend away from the perpendicular as much as the red light. And so what is white light all coming in, the red light's going to bend further away than the bluer light. And so you're going to see that this light spreads out and that redder light bends further away from the perpendicular than bluer light. And what happens is that you get this separation now. What was originally white light, white monochromatic light, now because of slightly different refraction angles, because of the light being composed of light of slightly different wavelengths, you're going to get some red, some orange, some yellow, some green, some blue, some indigo, some violet. Okay? That's the idea of dispersion. That's why if you shine monochromatic light into a prism, you get the rainbow coming out on the other side. And if you've been fortunate enough to see a rainbow happen in the sky, it's a similar phenomenon, except it's not a bunch of prisms up there, it's actually water droplets. And if you can imagine, if the conditions are just right, when light from the sun refracts into these water droplets, that light disperses into the color of the rainbows. And then that dispersed light bounces back off the backside of the droplet, and then it eventually gets back to our eye. And that's why you see the rainbow phenomenon. It's another example of dispersion, which once again, when we deal with the refraction of light, that is when light propagates from one medium to the next, you're going to get different rates at which the light travels. And it turns out that that also depends on the wavelength of the light. And so for monochromatic light, if it has a composition of red, orange, yellow, green, blue, indigo, and violet, and each of those colors have slightly different frequencies, which means they have slightly different wavelengths, which means they travel at slightly different speeds through a medium, then they're going to have slightly different refraction angles. And that means that the original monochromatic light gets dispersed out into the different colors of light that make it up.